So, hi everybody, welcome to this lecture on structural elucidation of nicotine. So, this is your third alkaloid that is there in the syllabus. So, let us go through its structural elucidation. So, nicotine is an tobacco alkaloid. So, it is that component in tobacco component, that makes smoking highly addictive, and its boiling point is 247 degrees Celsius. So it belongs to pyrrolidine, pyridine group of alkaloids. Okay. So let's do its structural elucidation. First, nicotine. इसका molecular formula होता है is C10, very important, C10H14 N2. Okay. So second point to be noted is its double bond equivalence, something that I'm sure you would have studied in when doing spectroscopy. Double DBE, double bond equivalence, is 5. Okay. So what is double bond equivalence? So double bond equivalence is given by number of carbon atoms minus number of hydrogen atoms divided by 2 plus number of nitrogen atoms divided by 2 plus 1. So here the number of carbon atoms are 10. So hydrogen atoms are 14. So it is 14 divided by plus the number of nitrogen atoms are 2 divided by 2 plus 1. So if we do the calculation, it is 10 minus 7 plus 1 plus 1. So this is 5. Okay. So what does double bond equivalence signify? What this number tells us is, see, if double bond equivalence is 1, it means there is one double bond or one ring. I'll just give you a brief idea. If there is one double bond, if your double bond equivalence is 1, if your dBE is 1, which means there is one double bond or a ring is present. Okay. Now if your dBE is 2, double bond equivalence is 2, which means there are two double bonds there are two double bonds or there is one triple bond or one triple bond or there is one double bond and a ring. So essentially you need to account for two double bonds or a ring. So that is out. So 5 double bonds if your dB is 5, which means there is three double bonds, a ring and a ring, another ring, or something, four double bonds, one ring, or three rings and two double bonds. So you do the permutation and combination. Okay, so that is what your dB signifies. So the dB for nicotine is 5. So let us account for those 5 dB. Okay, before that, one sigh of relief is this compound has no oxygen, which means we need not account for oxygen. So third, no oxygen is present. Okay, less work for us. Fourth, what is the nature of nitrogen? Let's account for nature of. Okay, A. So under this nature of, let's, so you apply whatever I have taught in the class. So let us see. So nicotine does not react with acetyl chloride or benzoyl chloride to give N acetylated or N benzylated derivatives. Okay, so C10H14 N2 reaction with this acetyl chloride RCOCl. It could be acetyl chloride or benzoyl chloride in presence of NaOH. No reaction occurs. No reaction. Okay. So what does this tell about the nature of nitrogen? So think B. Nicotine on treatment. Nicotine forms diquaternary ammonium salt when only 2 moles of methyl iodide CH3I are added. So what it means is each nitrogen has only taken 1 mole of methyl iodide. So both of these confirm that, let me just write the reaction that is there here. So C10H14 N2, when you react it with 2 moles of methyl iodide, gives you diquaternary compound. So C10H14 N2 CH3 twice and plus plus and 2I minus. Okay, so quaternary ammonium salt of nicotine. This is your diquaternary ammonium salt of nicotine. Okay, so what both of these confirm is both of these confirm that both the nitrogens are they primary, secondary, or tertiary? Fill in the blanks. They are tertiary in nature. Okay, only because they are tertiary in nature, they are able to react it with only 1 mole of methyl iodide. If they are secondary, they could react with 2 moles. their primary they could have reacted to three moles, right, to make it a quaternary compound. So because they are tertiary, they are only reacting with 1 mole of methyl iodide. So that's our first hint. Okay, so let us move to the next piece of information. Nicotine on oxidation with KMnO4 nicotine on oxidation with KMnO4 use nicotinic acid. Okay, so nicotinic acid is a pyridine 3 carboxylic acid, 3 carboxylic acid. Structure is this one. So this confirms that the basic nucleus of nicotine that the basic nucleus of nicotine is pyridine. This is where we come to know that there is a pyridine molecule that is present. So this also accounts for because there is a pyridine, okay, also accounts for the 4 double bond equivalence. See, there is 1 ring and 3 double bonds, so that accounts for 4 double bond equivalence. So now what is left is only 1 double bond equivalence, and that 1 double bond equivalence could be either a double bond or a ring. So let us find out what is it. Now what is the nicotine molecular formula? C10 H14 into, so nicotinic acid, the formula is C5 H4, and there is nitrogen and COOH, right. Now which means this means, now when did nicotinic acid form? Nicotinic acid was formed when nicotine was treated with potassium permanganate, KMnO4. What does potassium permanganate do? Potassium permanganate oxidizes the benzylic carbon, any benzylic carbon of the aromatic ring, to carboxylic acid. So which means this COOH group should have, in nicotinic acid, should have arisen from the remaining, after pyridine is accounted for, this formula. Okay, so which means your nicotine, the formula is something like this: C5H10N. Now we need to account for what is there here. Got it? Okay, let us move to the next thing, next experimental evidence. So nicotine on treatment with HI at 150 degrees Celsius gives methyl iodide so that confirms that there is a presence of N-methyl group in side chain. So this method is also called as Herzig-Meyer method. C4 H7 then CH3. Now this positive reaction shows that there is a presence of methyl iodide okay. This methyl iodide is treated with is absorbed on silver nitrate AgNO3 okay. So we get AgI. AgI is weighed okay, to find out how many N-methyl groups are there. If there is only one N-methyl group, it will give respective amount. Okay, so since only one, so by this method, so this is called Herzig-Meyer method. You can, it seems like I've taught it in class. Herzig-Meyer method. That's how we know that there is a N-methyl group in the side chain. Fine. What is the next piece of information? Okay. So that was 6. Let us go to the 7th point. Okay. Nicotine on treatment with zinc chloride treatment with zinc distillation Zn zinc chloride in HCl and on further reaction with soda lime decomposes. So this is what zinc distillation means. So zinc distillation decomposes, it breaks part by part. So decomposes to following. So C10 H14 into ZnCl2 HCl. So it forms C10 H14 N2. So it forms an adduct addition product ZnCl2 plus 2HCl and H2O. This on reaction with soda lime, heating will give you pyridine, it will give you pyrrole, and it will give methyl chloride. Okay, so this pyrrole, remember there we told that there is one double bond equivalence, it could be either a double bond or a ring. So this pyrrole confirms that what 5-membered ring is present in side chain. Okay, now between this and this we are short of 4 hydrogens, and so let us reconstruct what could be our molecule till now. So let us go back and see where was it that how many, what in the side chain, what are we supposed to account for? So let me use a different pen here. So in the side chain, is it visible? No. So let me take a green one. In the side chain, so we need to account for C5H10 nitrogen. Now we also told that there is a N methyl group, so it is C5H7. Sorry, let me go back. If there is a N methyl group, it is C4H7, and there is a N methyl group. So now, if this happens to be your pyrrole, which has been uh, one of the products in zinc distillation decomposition, so we are short of 4 hydrogens, right? So this is C4H3 and NCH3, right? Okay, so essentially forget about all this. If you are not getting this, that's okay. Just note that we are now short of 4 hydrogens. Short of 4 hydrogens. 4 hydrogens are missing. So could this pyrrole group that the genesis of that, the parent group, the parent molecule, be your pyrrolidine group? So this could be your pyrrolidine. So your side chain could contain not pyrrole ring but a pyrrolidine ring. So only then we can account for 4 more hydrogens there. Okay, so what is the structure of pyrrolidine? Simple, it's a saturated pyrrole. Okay, this is your pyrrolidine group, and see what are those 4 hydrogens that are, see pyrrole already has 1, 1, 1 and 1, right? So your pyrrolidine has H, H, H and another H. So that's how, so these 4 could be accounted for if we assume that it is not actually the pyrrole ring, it is the pyrrolidine ring that is present in the nicotine side chain. So let us see what is the confirmation that there is a pyrrolidine. So to confirm the presence of pyrrolidine ring, so this is point number 8. The presence of pyrrolidine ring in side chain is confirmed by by oxidation of nicotine isometeordite. See this structural elucidation is little lengthy compared to others. Nicotine iso. I'll just tell you what is the structure of that is. Meteordite in presence of potassium, ferricyanate, cyanate. Okay, the products are nicotine, which on further oxidation with chromium oxide in H2 SO4 gives hygeric hygeric acid. Okay. So this is the conformation for presence of pyrrolidine. Okay. So let me share with you the reactions now. This okay. So first nicotine isometeordite. What is this structure? Okay, isometeordite in presence of potassium, ferricyanate, K3, CN6. Okay, use nicotine. What is the structure of nicotine? This in presence of CrO3 in H2SO4 gives L-hygerinic acid. So this is your confirmation for the presence of pyrrolidine ring. Now based on the information that we have so far, okay, so the structure of nicotine could be either of these two. See, there is a pyridine ring, there is a pyrrolidine ring, and seems like, and there is a N-methylated group in the side chain. So it could be this. Okay, there is a pyridine ring, there is a pyrrolidine ring, and there is a N-methylated group. So this, or there is a possibility that the structure could be this. Okay, both of these are possible based on the information that we have till now. So to confirm the position of pyridine, so on pyrrolidine, so where is the position? So to confirm this position of pyridine on the pyrrolidine ring, so nicotine is bromine. So bromine in HBr, that gives dibromo 14. 14. 14. So whose formula is C10H8N2Br2O2. Okay. So which one further reaction with barium hydroxide? Use three products, so which is nicotinic acid, malonic acid, and methylamine. So let us see what structural elucidation we can do based on this information. So let me write the products here, write the reaction, accompanying reaction. Nicotine. Okay, so I'm just writing what was the C5H10N. Okay, so we need to find out the position of pyridine on pyrrolidine ring, right? That is what. So when you treat it with Br2 in presence of HBr, gives you dibromo-14E. Dibromo-14E. Okay, this is your structure of dibromo-14E. So this on further reaction with barium hydroxide. So BaOH twice distillation gives you nicotinic acid. Okay, plus malonic acid OH 2 plus your methyl amide CH2. Now let us account for, let us take the carbon structure here only and the important skeleton here. So first it should account for yeah, this. Now there is also a triple CCC from malonic acid, and then there should be your NCH3. Okay, these are the important things, right? Okay. So now this is possible. These products, the three products, these products are possible only with this particular structure. Okay. How it would have broken is, one, nicotinic acid should have come from here. Okay. Then the methyl amine should have come from here. Then your malonic acid should have come from this. There is a mistake. Should have come from this. Okay, let me change the color here. The last, take red. So your nicotinic acid should have come from here. Your malonic acid should have come. So this is possible with only this structure. It is not possible with, not possible. This skeleton is not possible with this particular structure. You can try it out. Not possible. See, there is, so it's not possible. So the correct structure for nicotine based on the arguments that we have is this one. Okay, this is your final structure, not this one. Okay, so this is your final structure for nicotine. So let me do it here one final time. Okay, okay. You see, everything is accounted for. There is a pyridine ring, there is a pyrrolidine ring, then there is N-methylated group, then the oxidation with KMnO4 gave you 3 carboxypyridine, which is nicotine, so which means this group, the side chain is attached at third position. Then there is 5 double bond equivalents, 1, 2, 3, and a ring here and another ring here. Then what else? So all the arguments, this structure is satisfying all the arguments that we have made. So this is your, and see, both the nitrogens are tertiary in nature. So yeah, so this is your correct structure. Thank you so much. See you all. Bye bye.